Welcome back, I'm that chemist, and today we have 5 important papers in organic synthesis for the month of December 2022. The first paper for today is a very important paper involving the haloboration of carbonyls. Some highlights of this paper include the conversion of aldehydes and ketones into alpha haloboronates. This involves the removal of the oxygen and the installation of both a halogen atom as well as a B-pin group. This is a 2-step one-pot process that features an excellent scope. Additionally, the authors demonstrated that enantioselective conditions were possible. Now, while this paper lacked an investigation into the mechanism, I would propose the following. First, B2-pin2 is able to be installed under catalytic conditions with copper. This affords this alpha B-pin boronate. Then, once a TMS halide is added, the TMS group is able to coordinate to the oxygen of the boronate, and this would make this into a better leaving group, and then the halide could displace this as a leaving group. Alternatively, the halide could coordinate to the CB boron, and this could undergo a 1-2 shift, simultaneously substituting the TMS-activated boronate as a leaving group. In this example, the nucleophile is shown as chloride, although the authors demonstrate that chloride, bromide, and iodide were all tolerated. This tolerated different functional groups such as this alkene, such as this thioether, this nitrile. You can see that chloride, bromide, and iodide are all shown here. There are many, many more examples in their manuscript, and I encourage you to go check the paper out if you'd like to see everything that was possible. Here we have saccharin, we have a derivative of a nucleotide, as well as these other 2 compounds, which were also derived from ketones. Now, if you're not familiar with some of the chemistry of boron, these building blocks are extremely useful. Sometimes you want to install different nucleophiles to a carbonyl, but then you get trapped with that pesky oxygen afterwards. But in this case, we can see that the oxygen is fully removed. And it's a lot easier to work with something like a B-pin or a halogen because you can do interesting stuff with those. So in this one example, the authors demonstrate that if you take an aldehyde in the presence of B2-pin2 with a TMS halide, they're able to get their corresponding chloride or iodide products where we have the B-pin and the halogen installed. And then under different conditions, you could diversify this into several different useful building blocks. If we wanted to substitute the halide, you can see that an aryl ring has been installed, here an alkyl chain, here a vinyl group has been installed, as well as some other interesting derivatives. Now, down here you can see these examples where the halide was left, but the B-pin group was substituted. So here we can see the B-pin has been substituted with an alkyl group. Here we've chloro-deborylated, or alternatively, a bromine or a nitrile were both able to be installed. So this is super useful. This is only a little bit of what's possible using this chemistry, and it's basically just limited by your creativity and the synthetic tools that we've developed as chemists. I mentioned earlier that they also demonstrated some enantioselective variations. So here you can see that depending on whether or not an aldehyde or a ketone was used, they needed to use different ligands, and they do this in fairly decent enantioselectivity, where examples with different functional groups were tolerated, although this was a smaller scope. There are more examples in their manuscript, and I encourage you to check that out. Now, in terms of applications, earlier I showed that you could selectively substitute one of the 2 groups depending on the conditions. In this example, you can first substitute the chloride. This is through the formation of an 8 complex and a 1-2 shift. This R group is able to shift and displace the chloride, inverting the stereochemistry of the boron. A subsequent alkylation can then occur, installing another R group in the place of the boron. So extremely powerful chemistry. Some examples of the conversion from this chloro B-pin to the Grignard substituted product are shown here. The B-pin is retained. And then these intermediates were derivatized into further products using different compounds as shown here. If you're interested in more details, I'd encourage you to go check out the paper. I personally find this chemistry extremely appealing because if you look at a product like 98, 99, or 101, which are shown here, you would not think to start from an aldehyde in that position with that R group chain over there. That's just not something we traditionally think about, especially not in an enantioselective fashion. So I was quite impressed with this, and I'd like to congratulate the authors for this excellent work. The second paper for today is another very important paper from the Agarwal group, and if you're not familiar with the Agarwal group's chemistry, I would encourage you to check out some of the work they've done. They have really demonstrated that boron is an extremely powerful element. While we traditionally think of boron being just used for cross-couplings, they challenge that narrative. I've done a video on the channel before discussing some of the basics of boron chemistry, and if you don't have a strong background in boron chemistry, this might be a place to start. I'll put a link to that in the description. Some highlights of this paper include a chemical masterpiece, an inspiring use of boron homologation. Additionally, they demonstrate the diastereoselective of 1,3-polyboronic esters, and they elaborate these polyboronates into the natural product Bahamolide A, as well as many other displays of chemical creativity. So in a nutshell, what they're able to do with their chemistry is add B2Pin2 across an alkene that installs 2 boron groups, typically with really good enantioselectivity. Then what they do is they use these metallocarbenoid complexes, which are able to form a boronate complex, and then undergo a 1,2 shift where the R group connected to the boron attacks at this red carbon and displaces this ester group as a leaving group. Now, it might be a little bit confusing. They started with a 1,2 diborane, and they end up with a 1,3 diborane, and that's because of the 1,2 shift that this undergoes. While the mechanism wasn't discussed in this paper, the 1,2 shift involving boron-containing compounds with leaving groups is well known, and it's also something I discussed in that video I mentioned earlier. Now, because they can keep doing this, if they install a terminal alkene, they can just add B2Pin2 across it again, and depending on the conditions that they choose, they can get different diastereomers. So effectively, they can install, in a 1,3 fashion, several different chiral centers, and then they can convert those to whatever they want. In this case, they've done an oxidation, and you can see this polyol product. As one example in their paper, they show this. Starting with compound 1, they get this elaborated compound 4. Under specific conditions, they can get this desired diastereomer. They can then do this diboronation, and depending on the conditions, they can get one diastereomer or the other, and then they can iterate this several times to get several different diastereomers of their products. If they start doing this with this diastereomer, instead of getting the 1,3 trans, they get the 1,3 cis, and then they get another whole library of compounds. So this is a really powerful tool for library synthesis, and it's also extremely useful in synthesis broadly speaking. I really look forward to seeing how this gets used in the future, and we haven't even talked about the whole purpose of this paper yet, a total synthesis. So the application of this chemistry to the total synthesis of Bahamolide was demonstrated. So initially, you can see that they form this magnesium carbenoid. This is able to functionalize one side of this selectively. This has got diastereoselective reactivity, and you can see that they do get a little bit of compound 36 where it's reacted with both sides. Now, they take the desired product, 35. They're able to do this chemistry on the opposite side of the molecule because this boron is less substituted. They only report reactivity at the terminus. They can then convert this polyboronate to the corresponding polyol and protect this with acetonides, and then they do a couple further steps to transform this to the natural product. Initially, they do an olefin metathesis to install a formal group where R is. This is just olefin metathesis with Heuveia grubs 2. And the next step is for them to do a Horner-Wadsworth-Emmons. So they do a lithiation of this phosphonate, which can then undergo a Horner-Wadsworth-Emmons with this aldehyde 37, which is where R is an aldehyde group. Then once they have this polyconjugated system with this acetonide-protected polyol, they hydrolyze the corresponding ester to the acid, and then they undergo macrolactonization to afford the natural product Bahamolide A in a total of 14 steps in their longest linear sequence. So this is a really impressive piece of work. I have one last thing I want to say about this paper, and that's that this chemistry is extremely useful. Here you can see that they're able to make all these different polyboronated compounds, and then starting with one of them, such as 41, they're able to convert this tetraboronate to this tetrakis furan, tetrakis thiophene, this tetrakis polyvinyl group, this tetrol, this tetrine, and once they get this tetrine, they're even able to do click chemistry, installing 4 triazole rings. Alternatively, if you don't want to do any of those other things, you can just install 4 acetyl groups. So this chemistry is extremely powerful, and I really like this figure, and I hope it demonstrates to you the possibilities of this chemistry. One final example that they have here is they show that you can convert this to the polyalkene, and then by doing ring closing metathesis, they're able to form this tetracyclopentine system, which is really impressive. So this chemistry is really awesome, and if you aren't convinced boron is useful yet, you should definitely go check out that video I mentioned earlier so that you can be really sold on the chemistry. You might be surprised to know that a lot of the chemistry that this paper utilizes was already reported, and a lot of reactions are reported in the literature, but just because they're reported doesn't mean that we're all familiar with it, which is why you should try Reaction Flash. Today's video is sponsored by Reaxys. Reaxys is my preferred chemistry information system for searching chemical reactions and related literature. They also have a free app for iOS and Android called Reaction Flash. Reaction Flash is an app with over 1,000 named reactions in organic chemistry, and you can quiz yourself on how these reactions work, what reactants are used, and what sorts of products are formed. I have specifically used Reaction Flash as a way to learn more reactions that may help me come up with new ideas for my research. The app allows you to view the mechanism of named reactions, test your knowledge with an interactive quiz, and search through numerous specific examples of these reactions from peer-reviewed literature. Thousands of students and researchers already use Reaction Flash. Reaction Flash is a great app as an up-to-date reference and learning tool for chemical reactions, so why not download it today and give it a try? You can download it on iOS or Android by clicking the link in the description. That way they'll know you came from here. I'd like to thank Reaxys for their support of this channel. The third paper for today is the conversion of cyclopentines to pyridines. They also demonstrate some other heterocycles can be prepared, but pyridines are the main highlight of their scope. So what they do is a nitrogen atom insertion into aryl substituted cycloalkenes, and this affords pyridines and other nitrogen-containing heterocycles. Now, one limitation of this method is that an aryl group is needed pendant off of this alkene, and while that might seem like a major limitation, the examples that they demonstrate in their paper are quite impressive. So the mechanism of this chemistry is as follows. Initially, cobalt-2 is able to oxidize TMS azide into an azide radical. They confirm the presence of an azide radical in trapping experiments, and this forms a cobalt-3 salt. Once this azide radical is generated, this is able to attack this alkene, forming a benzylic radical. This benzylic radical can attack at the azide, forming a terminal nitrogen-centered radical, which can then give off nitrogen gas to form the corresponding aziridine radical. This aziridine radical can ring open the 5-membered ring, affording the 6-membered ring with a nitrogen in it, and the next step is the reduction of cobalt-3 into cobalt-2 and the elimination of H+, forming this conjugated system. You can see that this is almost an aromatic ring, so it's conceivable that under the reaction conditions, this oxidation would be facile and the corresponding pyridine would be formed. So the demonstrated scope of this chemistry is fairly good. A number of different groups were tolerated on this arene. They mostly explored substitution in the pair position, although there are other examples that they did where the pyridine was more functionalized, such as in cases 22, 24, and 19. There are many more examples in their manuscript, and I encourage you to check it out. In addition to the pyridines, they were also able to form some isoquinolines, and so these isoquinolines were also able to be part of polycyclic systems, such as this pineapple-like species shown here, as well as more complex examples. So this could have some applications in material science, it could potentially have some applications in drug design, and I'll be interested to see how people use this chemistry moving forward. The fourth paper for today is the total synthesis of Luminomycin. There is a lot of creative synthetic chemistry in this paper, and the way that they got to this total synthesis was through degradation studies to probe the reactivity of naturally available Luminomycin. So their degradation studies were as follows. They initially opened up this maleic anhydride using diazomethane, and then they protected these two alcohols with mom chloride. Once this was done, they were able to open up this lactone with potassium carbonate and methanol via transesterification. The next step was to add in a thiol to this alkene at carbon 26, and they also protected alcohol 17 using TBS chloride. They were then able to cleave this thioacetal with silver nitrate, affording compound 21. And this is a compound that they wanted to access as an intermediate for their total synthesis. They were pretty sure if they could get this, that they'd be able to complete the rest of the synthesis. And so there's a lot of chemistry and a lot of stories in this paper. I'd encourage you to go read the full paper, but I'm just going to highlight some of the cool synthetic steps that piqued my interest. In this example, they take this intermediate 38. Using TBAF, they deprotect this TBS group and they oxidize it using manganese dioxide. When you have propargylic or allylic alcohols, it can be easier to oxidize, so manganese dioxide can be sufficiently strong. Then they take acrolein 39, they treat it with TIPS triflate in the presence of lutidine, and this quantitatively forms the corresponding TIPS enol ether. The TIPS enol ether is then activated using TAS fluoride. This deprotects the TMS enol ether, and a Michael addition of this oxygen at this center here was able to occur, and selective protonation at carbon 4 was accomplished using BHT. When they were trying to complete their synthesis, they had thought about closing this macrolactone first before doing an organometallic addition to this ketone, but they were running into issues adding it in. So they ended up making this ketone first, and they found it was necessary to add lanthanum to get the selectivity that they wanted. So using methyl lithium in the presence of lanthanum chloride, they were able to add in that methyl group, and I thought that that was kind of interesting because you don't see lanthanum used for these types of additions that frequently, although this is total synthesis, so we know how that goes. Another step that might be impressive to less experienced viewers is the use of a tempo-babe oxidation in the same pot as a pinnic oxidation, which was extremely selective for the primary alcohol, tolerating the secondary alcohol without any issues. So the way that this works is this oxidizes the primary alcohol to an aldehyde, and then the corresponding aldehyde can be oxidized via pinnic oxidation with sodium chlorite. If you're not familiar with the pinnic oxidation, I also have a video about that, and I'll include a link to that in the description. Now, I've cut out a lot of the synthetic steps involved in their paper just for the sake of time. Once they had intermediate 21, which was that initial compound that we talked about earlier, they were able to go forward with it and complete their synthesis. So using compound 67, which was actually a 9-step synthesis that they outline in their supporting information, they were able to form this thioacetal species, and then using silver triflate, they were able to eliminate it to afford the corresponding vinyl ether. I was impressed with this way to form a vinyl ether because vinyl ethers are one of those challenging things you don't see synthesized too frequently. The next step was to deprotect this TBS group, as well as this TMS ethanol ester, and that unmasked both the alcohol as well as the carboxylic acid. They then explored several different macrolactonization conditions to form this last macrolactone, and the last step was to deprotect these two mom ether groups using HCl in dioxane, affording them with Luminomycin. So this is a really cool paper. If you like interesting chemistry, you should go check out this paper. And yeah, this is a really sensitive looking product. I mean, look, we have a maleic anhydride, we have two macrolactones, we have a vinyl ether, as well as this polycyclic scaffold. So very impressive overall, and I'd like to congratulate the authors on this work. The fifth and final paper for today is Allylic CH Amination. Some highlights of this paper include palladium-mediated allylic CH amination. This work utilized an external aryl bromide as an oxidant, and they needed to screen different bromides so that they were able to avoid any potential cross-coupling with that arene. In this work, the amine is their limiting reagent, and their justification for that was to just kind of keep hydrogen atom transfer going. The proposed mechanism of this work is that initially, under photochemical conditions, the aryl bromide would be able to oxidize the palladium-0 species that they have to palladium-1. This would generate an aryl radical that could abstract a proton, forming this allylic radical species. This could then engage the palladium-1 to form a palladium-2 pi-allyl species, which could then react with the amine, forming the corresponding allylic amine product. You can see their preliminary results here were that their ideal solvents were benzene and benzonitrile, although they also found some success with sulfolane. Additionally, they used tetrabutyl ammonium bromide as an additive, although I couldn't find anywhere in their paper where they discuss the importance of tetrabutyl ammonium bromide in this work. As additives go, you add them to the reaction and they add to your yield. Some examples of alkenes that were functionalized with this chemistry are shown here. This worked for styrenes as well as alpha-beta unsaturated carbonyl compounds, but it did work with other alkenes, such as this unactivated alkene 42. The presence of heterocycles were tolerated in the case of 29, and when they used other amines instead of piperidine, they were still able to get conversion to their desired products. They also explored some non-aliphatic nitrogen-containing nucleophiles, and this was another really impressive demonstration from this work. I also wanted to briefly mention that they have some enantioselective variants of this in their paper, but the EEs aren't stellar. So if you'd like to see those, I'd encourage you to check out the full paper. So in addition to the 5 important papers for the month, we have some honorable mentions, including the conversion of pyrimidines into pyrazoles. We have the aminoacylation of olefins, a multi-component annulation reaction with rhodium-3, the synthesis of fluorooxazoles from a difluorovinyl iodonium salt. We also have the thioanthrination/oxidation of olefins to the corresponding acrylines. We have an asymmetric acylloin synthesis, and we have the metafunctionalization of highly substituted phenols. Last but not least, we have the remote oxidation of internal alkenes, where starting with an internal alkene, the authors were able to synthesize a terminal alcohol, which was kind of cool. So hopefully you've enjoyed this month's episode of Important Papers in Organic Synthesis. If you think that there's any important papers that I didn't cover, you should leave a comment down below with a link to that paper. Thanks for watching, and I hope you have a great day.